Alright, hello and welcome to the first set of demos for optics. What we have here is a setup that is going to demonstrate the use of Brewster's angle and Fresnel equations, and we're going to plot a curve eventually from the data, which we may not be seeing now, may be seeing later on. Before we go further, I'll just take a quick do a quick review of the setup that we have here. So I have a helium neon laser rod right here. It's 635 nanometers going through a polarizer. It's transmitting only the parallel polarization through this, hitting a microscope slide, and light is being transmitted out, and it is incident at the Brewster's angle. So we'll talk about this later, but right now we do not have any power reflected off to the other photodetector. These two are our photodiodes. They are producing a voltage proportional to the power hitting them. This is PD1 or photodetector 1, giving me V1 proportional to the power hitting this. It's going to the scope, channel 1. The scope is over there. And PD2 is giving me V2, which is going to the scope, channel 2. So we have the polarizer sending out a parallel polarization. So the screwdriver kind of points it in this direction or that. Anyways, so what I would like to emphasize is this is a ratio measurement, so we need to take a reference measurement before we start. So initially when I started out, I removed this microscope slide and measured the power of the parallel polarization hitting this guy, and found that my voltage was 10.5 volts. And later on, then I put this thing in. So now I'm getting the voltage with the slide in it, so I can take a ratio. So what I have here is I have a parallel polarization hitting at Brewster's angle, which is 56.3 degrees for glass, and light bouncing off over there. Now the speciality of Brewster's angle, as we hopefully all know, is that if you have parallel polarization hitting a surface at the Brewster's angle, then you do not have any light reflecting. You have all of it going through. Ideally, it's all of it. Practically, the reflected light goes negligibly down to 0. So if you look at channel 2 right here, and let's take a closer look at the scope screen. We have channel 2 right there. So channel 2 is almost down to 0, and channel 1 is at 10.5, which is equal to the reference voltage that I measured without the microscope slide. So we can make a very logical assumption that all of the power, or almost all of the power, is going straight through at the Brewster's angle. Now, why or how do I know that this is transmitting parallel polarization out? The reason I know this is I set this microscope slide at 56 degrees and adjust it so that any light reflecting from this would hit this guy. And then I rotate the polarizer right here so that I can adjust my polarizer angle based on the power level on this thing. What I mean is that when I rotate this, at the parallel polarization, whenever I'm transmitting parallel polarization, this power level should go down to 0 or be negligibly small. So I'm going to rotate this guy gradually, go up and go to perpendicular, and we'll see that the power level at this thing would actually go up, and then we'll come back to this location again. So we'll always we'll try to do this every time before we do an experiment based on that. So if you can see, then as I rotate this thing, it might be a little hard to see. We probably need a bigger screen, but and so I rotated it. Now it's parallel perpendicular polarization transmitting through, so we have a peak at the power, and I gradually rotate it down, and I rotate it so that I get almost negligible power. Ideally it should be 0, I just want to hit the minimum. So I have the minima right there. So now I'm sure that the power level of channel 2 is close to 0, so I'm transmitting parallel polarization and there's no light reflecting on this guy. So now what do? I adjust this thing to go from 0 to 90 degrees, 87 degrees rather, and we plot, we first take the voltage values of this guy for each incremental angle, and eventually we'll plot the power transmission ratios. So what I'll do is I'm going to move this guy so that I have 0 degree incidence. So now we have 0 degrees, and at 0 degrees we can see that the microscope slide is at normal incidence, and we have about 10 volts hitting 10 volts worth of power hitting the photodetector 1. So that's our normal incidence power, and so the transmission coefficient for power at this point would be this voltage divided by our reference voltage. This voltage being 10 volts, reference voltage being 10.5, so we do 10 over 10.5. It should be around 98%, 92% hitting this guy and 8% going back. So what I'll do is I'll increment the angles by 10 degree increments to a certain point, and eventually then we go to smaller increments. What we expect in this case, we expect a relatively constant power level as I go from 0 degrees to close to the Brewster's angle. As I cross the Brewster's angle, we expect a sharp exponential decay in our transmitted power. So I'm going from 0 to 10 degrees. So the power level is at 10 degrees. If we can look at the scope a little bit. So the power level is at 10 degrees right there, 10 volts, I'm sorry. 10 volts right there. It's a little higher than 10 volts. We can see it went up a little bit, and we expect it to. We expect it to go close to 10.5, and that's the maximum at Brewster's angle. So we now go over to 20 degrees. It's still at 10 volts. It went up and went down, so it'll be something like that, something close to 10 volts again. Next, I'm going over to 30 degrees. It's still close to 10 volts. Going to 40. Maybe a little higher now. It's approaching 10.5 again, a little bit. So at 50, we expect it to be a lot closer to 10.5. It's very much close to 10.5. So because we are very close to the Brewster's angle, at 56 would be exactly at 10.5. So since we have already done that, I'll just go straight over to 60 degrees. So 60 degrees, we're still at the Brewster's power. It's probably a little lower, but it's almost close. And as we go higher than 60 degrees and gradually to 70, 75, we'll see a stark decrease in the power hitting the transmission photodetector. So this is 70 degrees right here. So now we can see that the power is around 9.5 volts. Now please remember, I keep saying that the power is 9.5 volts or 10 volts. The volts is a proportional output voltage that is proportional to the optical power. The optical power is in the units of power, milliwatts. It just is the way the photodiode converts the power from milliwatts, and it ends up giving us volts proportional to the power. Okay, so now we have 70 degrees. We have around 9.5 volts. We go to 75. So 75 is 5, 6, 7, about 7 volts right there. So you see, as I'm increasing above 60 degrees or above 56, there's an exponential decrease in that transmitted power coefficient. Okay, so that's 75. Now we go to 80 degrees. So now the power is a little less than 6. We can say it's 6 or 5.5 volts. Channel 1 is at 5 volts per division, and channel 2 is also 5 volts per division, but just for now we are concerned with channel 1, so channel 1 is 5 volts per division, so that's 6 volts right there for 85 degrees, or 80 degrees, sorry. So now I'm going on to 85 degrees. There's a very sharp decrease over there. So this thing was 75 to 80, this is 80 to 85. So you can see that it's close to the zero, the ground level. So it's like 2 volts right there, and or 2.5 rather for 85 degrees. And we would like to focus our attention to this thing. See, this is the grazing incidence condition, where the light is grazing the surface. So at this point, we are approaching the condition where most of the light is reflected as opposed to being transmitted. And this is a condition that we will see in the next step also at 87 degrees, where we have a very bright reflected spot and almost no transmitted power. So I'm going over to 87. So at 87 we have like half a volt hitting the photodiode, and that is probably the last set of data, but we'd like to focus on this point right here, which is a very bright spot. That is the reflected power. Now the reflected power is so bright, it's almost all of the power, and that is the case for grazing incidence again. And like I was talking about it before, there's almost all of the power is reflected and very small amount gets transmitted through. So that would be Fresnel equations, and if you want to plot the curves, if this is V1, then we do V1 over Vref for each angle, so the angle becomes in the x-axis, and V1 divided by Vref goes to the y-axis, and eventually we plot a curve on that, and that will be equal to T. V1 over Vref becomes T, and if you want to find R, then R becomes 1 minus T, that's the reflection power coefficient. In general, the transmission curve should go like that, and the reflection should go up like so. And that would conclude this half of the demo, and then we'll go on to perpendicular polarization in the next set, and probably some more videos in the future. That'll be all. Thanks for watching.